To find the closest star to Earth, you have to look past our Sun and deep into the southern sky. At 4.24 light-years away, a red dwarf named Proxima Centauri holds the title of our nearest celestial neighbor. 4 light-years might sound like a short walk in cosmic terms, but that translates to roughly 40 trillion kilometers. If we sent Voyager 1, our fastest spacecraft currently traveling through interstellar space, toward Proxima right now, it would take about 73,000 years to get there. That is a journey longer than the entire recorded history of human civilization. Despite that immense distance, astronomers in 2016 detected something orbiting this star, Proxima b. It's a rocky exoplanet with a mass roughly 1.17 times that of Earth. Even more compelling, this planet sits squarely in its star's habitable region, often called the Goldilocks zone. This is the precise orbital band where temperatures are mild enough that water can exist as a liquid, which is the absolute baseline requirement for life as we know it. But Proxima Centauri's habitable zone looks very different from ours. Because the star is incredibly dim and cool, Proxima b has to hug it tightly to stay warm. It sits at just 5% of the distance between the Earth and our Sun. At that extreme proximity, the rocky planet is moving so fast through space that a full year lasts only 11 days. We have found the closest potentially habitable world in the universe, yet its extreme proximity to its host star guarantees an environment wildly different from anything we experience on Earth. Proxima Centauri belongs to a class of stars known as red dwarfs. It is tiny. If you pictured our Sun as a basketball, Proxima would be roughly the size of a golf ball, measuring in at just 12% of the Sun's volume. Because Proxima b orbits so close to this small star, gravity forces it into a state called tidal locking. Its rotation matches its orbit perfectly. One hemisphere is trapped in a permanent, scorching day, while the opposite side is locked in an endless, frozen night. If biology exists here, it is likely confined to a narrow strip of permanent twilight, dividing these two extremes, known as the Terminator Zone. Instead of a global oasis, this promising planet is a fractured world. It consists of 2 deeply hostile hemispheres, separated by a thin ring of stability, where life might cling to existence. The climate is only the first hurdle. Red dwarfs are notoriously active, and Proxima generates magnetic storms that make our Sun look entirely peaceful. When our Sun threw a major tantrum in 1859, an incident called the Carrington event, the resulting solar storm was strong enough to fry telegraph networks across Earth. Proxima's outbursts are significantly worse. In 2019, astronomers recorded a flare that caused the star to become 14,000 times brighter, unleashing a wave of lethal radiation directly at Proxima b. The surface is subjected to constant bombardment. However, life has a proven track record of enduring extreme hostility. At the bottom of Earth's oceans, we find bacteria thriving on hydrothermal vents, multiplying in complete darkness and water temperatures exceeding 400 degrees Celsius. We also find complex microbial networks surviving under kilometers of crushing sub-zero ice shelves in Antarctica. If Proxima b managed to hold on to a thick atmosphere, or if it generates a strong magnetic field, it could deflect the worst of those stellar flares, giving deep surface or aquatic life a chance to evolve in the dark. To know what is happening on Proxima b, we must look directly at it. That requires solving the 40 trillion kilometer problem, which is the central goal of an initiative called Breakthrough Starshot. Launched in 2016, the project was backed by some of the brightest minds in physics, including the late Stephen Hawking. It is heavily funded by entrepreneur Yuri Milner, who committed to designing a completely new method of deep space travel. The plan avoids massive rockets. Instead, scientists are engineering star chips, microprobes weighing just a few grams, roughly the size of a postage stamp. They will be attached to ultra-thin light sails and accelerated into space by an array of powerful ground-based lasers. The concentrated light will push these probes to 20% of the speed of light. At that velocity, transit time to Proxima Centauri drops from 73,000 years to just 2 decades. We are moving past theoretical physics and actively designing the physical hardware required to reach another solar system. There is a highly practical reason to map this neighboring system. Red dwarf stars burn their fuel incredibly slowly. Our sun will expand and consume the Earth in about 5 billion years. Proxima Centauri will keep burning for another 4 trillion years. That makes this tiny star system the most stable, long-lasting real estate in the observable universe. Any civilization that takes root there has nearly infinite time to evolve. It is entirely possible that an advanced species on Proxima b has already detected the chemical signatures of our water and oxygen and is currently looking back at us. Proxima b forces us to look outward. It is our nearest target, a potential future lifeboat, and our required first step if we are ever going to leave our solar system and survive among the stars.